Hi everybody, my name is Matthew Chinchilla and I am excited to be with you here today to talk about wind turbine active power forecasting. So let's get in. So what is turbine active power? Active power is the useful component of the product of voltage and current the turbine provides to the purchaser grid system, and it's generally measured in megawatts. Energy providers need to understand turbine power production potential. They need to understand, how much power can I expect from my turbine at any given time. And it's important for regulators to understand the active power production of a turbine so they can plan for seasonal events and maintenance schedules and things like that. Let's talk a little bit about the data that was used. So the turbine data that I have came from a Kaggle data set for a single wind turbine recorded from January 2018 to March 2020. The original data were readings that were recorded at 10-minute intervals, and the data set featured different features, including weather data, data about the turbine itself, and data about the rotor positions and other related rotor data as well. So the original data had some data quality issues. What you're seeing here is a chart that shows the percentage of missing rows for each of the different variables in the data set. So everything in blue means that the data was okay, and where you see red, that means that the data was, there was a lot of missing data there. So based on that, we pulled together a final aggregated data set. We used the six features, the 6 columns with the most usable data. They were considered for our modeling. We took the data that was taken at 10-minute intervals and we converted it into daily data to make it easier for us to base our predictions, kind of on a daily prediction instead of a 10-minute prediction time frame. So the final data frame consisted of 746 rows. That means we had data for 746 days consecutively. That when we looked at the overall data sets, we found that wind direction and nacelle position records had the same value. So we decided we would just drop one of those, and we dropped nacelle position, kept wind direction. And our final aggregated data frame consists of date, active power, reactive power, wind speed, ambient temperature, and wind direction. So these are the features that we'll use to do our model. So here is a plot of the active power realizations. Those red dots mean the daily aggregate output or active power from the turbine. Here's another look at that data that's been consolidated at the monthly level, and you can see there's some peaks there in July, August. So right here we're looking at the active power ACF and frequency charts. What these are showing us is on the left, that ACF chart. You can see kind of those lines are slowly dampening down. That tells me there may be some seasonality in here. And in the frequency chart, there's a peak at 0, which would indicate that the data is, there's wandering behavior in the time series data. So the modeling we're going to do is we're going to look at univariate models. These are models based on just active power. We're going to look at an ARMA and ARUMA model. And we're also going to look at multivariate models. This is modeling based on active power and the other recorded variables, such as wind speed and temperature. So we'll look at a VAR model and an MLP model. First model, the ARMA model, what you're seeing here in blue, where the predicted forecast that the ARMA model had, and the black line would be the actual actuals. So here the 30-day forecast isn't terrible, isn't great. At 120-day forecast, as we start to get out in time, it just starts to kind of dampen down to the mean. So not a great 120-day forecast for the next, we have the Aruma model. Aruma model brings in some seasonality trends into it that help with the predictions. So the 30-day Aruma forecast also wasn't that great, not terribly awful, but we can see that the 120-day Aruma forecast seems to be a little bit better. We seem to catch more of the seasonality, more of kind of those peaks and valleys, and it doesn't just damp off into the mean. Next, we looked at our multivariate forecasts. The first was a VAR model. This model really loved to just kind of stick to the mean. Wasn't all that great in either the 30 or the 120-day. And finally, we have our MLP model. This is a neural net based model, and it was kind of all over the place. Not real great in 30-day forecast or the 120-day forecast. So when we did a model comparison, you can kind of ignore I guess you can't ignore the numbers, but what we're looking at here is the ASE, the average squared error, and the lower these giant numbers are, the better. So when we do a model comparison, we can look at a lower VAR or ASE, and this can help us decide of the models what may be performing a little bit better. You can see in the 30-day ASE, but you can't always just base everything on this, because it shows that the ASE for 30 days with the lowest was the VAR model, but when we looked at that chart, we could see that it wasn't the greatest. And also in the 120-day forecast, we can see that the lowest we get here is the ARMA model, and its 120-day forecast, when we looked at the actual forecast versus the actuals, wasn't that great. So ASE can give us an idea of what may be a good model, but really another technique that we tried when we were doing this was ensembling a model, which is basically taking the average of the two forecasts. In this case, we took the ARMA and the Aruma models, and we got an ensemble model for those. We got pretty low ASE for both 30 and 120 days, and it seems to be kind of our best strategy. Our recommendation is to use an ensembled ARMA and Aruma model, and here you can see the 30-day ensemble model forecast. It's fitting our line much better, and the 120-day ensembled ARMA Aruma forecast looked so much better. So that's what we recommend, is an ensemble model. Thank you very much for listening.